Buongiorno tutti. I'm very happy to be here in Italy. I'm happy to have permission to travel here despite COVID problems. And my stay here at Chieti Pescara has been very productive and very enjoyable. I'm happy to share this webinar with you today and hope it will be useful to you. I'm hoping in the future that we have opportunity to meet in person and talk together as things improve in the world. This is my photo of my university, Brigham Young University. We are the second largest private university in the United States with a student body of about 35,000. We're located right against the Rocky Mountains. There's about 1,000 meters of vertical offset due to faulting. So we're very concerned about earthquakes here. 80% of our population lives within 20 kilometers of this fault line. This is the state of Utah. In case you didn't know where that was, we're close to California. Many of you might recognize better. It was the site of the Winter Olympics in 2002. Utah is well known for the national parks that are there, like these natural arches, these erosion features at Bryce's National Park, and sandstone cliffs at Zion's National Park. You can walk through Zion's through these narrow canyons with rock up to several hundred meters above you. It's very fun. We've noticed also some similarities as we've been in Italy to some of our national parks. In Venice, we saw all these narrow canyons as well that the gondolas like to drive through. And we have narrow slot canyons that we saw in Venice as well, where maybe one person could move through the Cale. And in Utah, we have these very narrow slot canyons that are quite beautiful as well. So I'm going to look at two different topics. One is increasing lateral resistance of deep foundations using ground improvement, and this will focus mostly on clay foundations, piles in clay, soft clay usually, and then I'll talk about ground improvement methods for liquefaction mitigation. This first topic is work that I did with Dan Brown and Hubert Law, who are prominent geotechnical engineers in the United States. So there are a number of occasions where we have to have lateral resistance for pile groups. We need to be able to deal with wind and waves in hurricanes. We need to deal with lateral forces due to seismic activity. We need to deal with ship impact. You may not think this is a big problem, but Google tells us that every 2 years there's a ship impacts a bridge and causes more than $2 million of damage. This was a surprise to me. Also, we may have to deal with lateral spread in earthquakes, like this bridge in Costa Rica that was pushed into the river, or other types of landslides like this pile group here. If you have to increase the lateral resistance for piles for an existing structure, or even a new structure, because of inadequate lateral resistance, you might try a structural solution. You could increase the number of piles and connect all the piles together with a pile cap. And this would give you the capacity that you need. An alternative would be to use a geotechnical solution where we improve the soil underneath the foundation and around the piles. Now, how would this work? Well, we know that most of our lateral resistance on piles comes within 5 pile diameters below the top of the pile. So we might only need to improve the depth equal to 5 times the pile diameter B. So how far out would we need to improve the ground? Most of our lateral resistance comes within about 4 to 6 pile diameters from the face of the pile. So for a very small zone of improvement, we may be able to produce significant increases in lateral or horizontal resistance. If we already have the foundation constructed, then we may only be able to treat around the edges of the foundation easily. So we could look at a solution like this. Some of the source of our increased resistance could be due to passive force against the pile cap, or it could be increased lateral resistance in the piles below the cap. Our philosophy is that one good test is worth 1,000 expert opinions. This was the statement by Wernher von Braun, who's the designer of the Saturn V moon rocket. And this is not because he was opposed to experts. We all want to be experts. That's why we come to meetings and webinars like this. The idea is that we first need to understand how the world really works. And once we've got this ground truth information, then we can fit our theories to match reality. Although I should say we need to have a healthy skepticism for test results. They're not all equal. Einstein said a theory is something that nobody believes except the person who proposed it. And an experiment or a test is something that everybody believes except the person who performed it. So maybe you've had some tests like this yourself where you're not completely certain that everything was done right or the result is really representative of the behavior of the material. I found both of these quotes on the internet, and I also found this one from one of our more famous American presidents, saying the trouble with quotes on the internet is that it's difficult to discern whether or not they are genuine. So maybe all these quotes are just altogether wrong. We received funding to do this study on ground improvement around piles from the U.S. Transportation Research Board, and we also had support from ground improvement contractors Hayward Baker, which is now Keller, for jet grouting and soil mixing, and rammed aggregate piers from GeoPier Foundation Company. Our test site is located in Salt Lake City, Utah. Our approach was to conduct full-scale lateral pile group tests with a variety of soil improvement methods to evaluate the improvement in lateral resistance we could obtain. Then, using these tests, we wanted to calibrate numerical models and perform additional virtual tests, you might say, to evaluate different treatment parameters and geometries. Then, using the results from the field tests and the numerical models, we want to develop a simplified model that can be used in design. This is our test site, which was located in a interchange for a large highway through Salt Lake City. This is a soft clay profile. The profile is consistent across the site, as you'll see. There's a gravel surface layer so that heavy equipment could access it. There was access to water, which we needed, and we could get approval to drive the piles and use soil improvement methods. So we have 16 lateral pile group tests that were performed. We did a test in untreated virgin clay for comparison. We did tests with compacted fill, jet grouted soil mixed treatment, flowable fill, and tests with rammed aggregate piers. I'm going to focus on tests with these 3 types for this presentation. If you would want to have detailed information about what I'm going to talk about in this part of the presentation, you can use this link to get the final report for our project, nap.edu/14574. So our soil profile is primarily a clay site with some sand layers and lenses, primarily clay. The PI is around 20, and the liquid limit around 40, so we have a plasticity index of 15 to 20. We've computed undrained shear strength from unconfined compression tests, Torvane tests, and the CPT. And a typical design strength is about 50 kPa in the top 1.5 meters. And then in the zone of interest, maybe down to 4 meters or so, we're looking at something like 15 to 20 kPa. It gradually increases with depth flow there. One thing we're concerned about was how uniform the soil profile was. So we did CPT tests at each of the pile group locations. And you can see that it's very consistent where we see the little sand layers. So that allowed us to make comparisons from site to site. In the first, our pile group is composed of 32 centimeter diameter steel pipe piles with concrete fill. They're spaced at 90 centimeters on centers, which is about 2.8 diameters. They're enclosed in a pile cap that's 3 meters square and 0.75 meters deep. The cap is poured flush with the soil in the front and the back, but there's a gap on the sides here and here. This is a plan and profile view of the test setup. There's a core bell, a concrete block that allows us to load the piles at the surface without influencing the soil below the ground. And we have two hydraulic actuators that can develop about 2,400 kilonewtons each with extension rams. So in this first test in untreated soil, we pulled the pile together, two pile groups together. And in the second test, we pushed the pile groups apart. This allowed us to get the difference between resistance with and without soil against the pile cap. This is a photograph of one of the test piles set up. The soil has dried at the surface, but the water table is within 10 or 20 centimeters of the ground surface. Here's the hydraulic actuators and the extension rods. So these are the two load versus deflection curves in each direction for cap 1 and cap 2 as they were pushed, pulled apart or pulled together. It's hard to tell how they compare, so what I'm going to do is adjust them so you can see them both in the same direction. So we loaded up to 120 kilonewtons at a deflection of about 40 millimeters. And those two pile groups are almost identical. This was a big surprise to me because as a geotechnical engineer, I've learned to expect things to be different and to see variations, sometimes substantial variations in short distances. But this was a good indication for us. So we loaded incrementally, and then we did some cyclic tests to see how the soil would behave. So our first test was to use compacted granular fill. So we excavated out a layer about 90 centimeters thick and backfilled this clay layer with compacted sand. So on the sand extends about 1.8 meters on one side and about 30 centimeters on the other side in front of the piles. So since this was adjacent to a soft clay profile, you can see here, we had some cave-ins and we didn't want to have students or workmen down inside here during this compaction. So the compaction was done with this compactor on the end of an excavator. And we were able to get the density to 16.3 kilonewtons per cubic meter, about 94% of the modified Proctor maximum density. A little lower than we would normally do. And this shows the compacted soil around the piles just before we poured the concrete cap. So what did we find out when we did the load tests? Well, for the fill that just extended 30 centimeters in front of the pile group, we had a 10% increase in lateral resistance, fairly small. And the fill extending 1.8 meters in front of the pile cap caused a 20% increase in lateral pile group resistance. So pretty small values, but the effort required to achieve those increases was also very low and of low cost. So we did some additional testing with compacted fill to look at other alternatives. So this is a 15 pile group. We first had a load frame loaded in one direction. Then we excavated 90 centimeters of the clay and then compacted sand so that we had about 2.4 meters of compacted sand. Then we put the load frame back in place and pulled the pile again. This plot shows the total group load versus deflection for the native soil with clay and for this test with sand. So what was the result? Now we're seeing about a 30% increase in lateral resistance for very small effort, really. Now, the increase largely depends on the difference between the strength before and after. So we also did some virtual tests. If we were to take if our soil profile consisted of sand with the undrained shear strength of 25 kPa, we'd have this load deflection curve. And if our sand was compacted to a little higher density, then we would expect this load deflection curve. So with this softer clay and the denser sand, now we're seeing increases. We'd expect increases of as much as 100%. So this could be a substantial increase that would be very beneficial to the lateral resistance. So replacing clay with compacted sand can increase the lateral resistance at very low cost. The strength gain on the piles depends on the soil strength contrast. We were seeing a 30% increase by replacing 45 kPa strength clay with sand at 93% compaction. And we're seeing a 100% increase if we were to replace clay with the strength, undrained shear strength of 25 kPa with sand and gravel at a 95% compaction. The next approach is much more expensive. This is jet grouting, which we use to mix the soil with cement and water. In this case, we're treating underneath the foundation. We had 8 columns. They're designed to produce columns of soil cement that are 1.5 meters in diameter. And with this geometry, we could largely enclose all the piles within this concrete block. The improvement zone extended 0.75 meters in front of the pile cap, so this direction, and it was 3 meters deep below the pile cap. Then we had another test where we did jet grouting only on one side of the pile group. So for each of these, the column diameter is 1.2 meters, and they interacted to produce a zone that was 4 meters wide and about 2 meters in front of the pile. And we're again treating to a depth of 3 meters. So pretty modest treatment depths. This shows the jet grout drill. Inside the drill rods, you have two pipes. The grout comes down the center pipe and the air comes out the annular space here. So the air jet keeps the slurry jet in place as the soil is being mixed. We used a cement with a or mix to produce a cement content of about 20% by weight. To evaluate the strength, we took wet grab samples of the soil that was mixed. Our soil before treatment, like we were talking about, had an underrange shear strength between 10 and 30 kPa. And after treatment, we're seeing something like 4,000 to 5,000 kPa. Now there's a large variation in the values that you get. So many times people will use a strength that's maybe 2 times less than the average wet grab sample. So they might use a value like this, maybe 1,500 kPa for the design. Now there's one last technique we used, which was soil mixing. And soil mixing was performed on this opposite side of the test pile. And it doesn't extend into we couldn't extend that in to touch the pile itself, but with the jet grouting, we can extend underneath the pile cap and connect the jet grout soil to the pile. Now, jet grouting is just one way to improve the ground or to mix the soil with cement. There are other techniques for mass mixing, like this alu alu excavator attachment that's made by a Finnish company, which can treat the soil almost continually to depths of 2 to 5 meters. Here's a photo showing that mixer in operation. In our case, we just used a conventional Trackhoe, a conventional excavator, and mixed the dry cement with the soil that was already saturated in a narrow zone in front of the pile cap, which you can hardly see here. But the cement content was, again, 10% by weight. And this produced a compressive strength of about 1 megapascal based on core samples. So let's look at the effect of these treatments. Let's first look at the soil mixing, where we have improvement just on one side. The red curve is the untreated soil, and the blue curve is the soil mixed wall in front of the pile. So we're seeing an increase of about 750 kilonewtons, which represents a 60% increase relative to the untreated soil itself. So that's a pretty substantial gain with very minimal effort. How does that compare with what we would get from jet grouting? I've plotted the untreated soil, the treatment with soil mixing, and then the load deflection curve for the jet grouting. Now we have a tremendous increase of 2,200 kilonewtons for this 9-pile group, which represents a 180% increase in resistance. That could be very substantial and very beneficial. I'm also plotting the jet grout, the test with the jet grout just on one side of the cap. And we almost got as much resistance with this as we did with the jet grout underneath, which was kind of rather surprising to us, but we'll see why that worked out that way later on. So this represented a 170% increase, or about 1,800 kilonewtons of increased capacity. So we're seeing that soil mixing and jet grouting can produce substantial increases in lateral resistance. Now you might be asking yourself, as I did, how many additional piles would be required for the same increase in resistance? Well, for the soil mixing approach, we'd have to double the number of piles that we had originally in order to get that same capacity increase. And for the jet grouting technique, we would have to triple the number of piles to get that same increase. Now, of course, as you add more piles, you also require a larger pile cap, which adds to the expense. And to mobilize teams to do the structural work to connect all the piles to the existing pile cap is a relatively difficult process. So our conclusion was that soil improvement could significantly, be more economically done than adding additional piles. So we took the results from these field tests and modeled them with the Ud'A computer program. It's symmetrical for a half model. There's the von Mises failure criteria that we're using. We took the shear wave velocity that we measured at the sites and reduced it to 25% for our stiffness to evaluate stiffness at larger strains. The strength was from the undrained shear strength profile I showed you previously, and we had a gap model to include behavior adjacent to the piles. So with a little adjustments, small adjustments, we were able to get good agreement between what the computer model predicted as the blue curve and what was measured with the red and red data points. This is for the virgin clay, and this is for the zone of soilcrete in front of the pile cap. And we also found out that it didn't make much difference how strong that mixture was, as long as it was above about 1 megapascal. And this is the result for the jet grouting case. Again, we're doing quite well on matching what actually happened. So now we could do some parametric studies. We could look at different cases with different thicknesses of treatment. And you can see as we make the thickness of improvement greater, we see increased resistance, but it's becoming less beneficial the deeper we go. It's more important at the shallow depths. Then a similar thing here adjacent to the pile cap. So we can plot the improvement for adjacent to the pile cap where we're not touching the wall. We have a moderate increase as we go deeper in the ground. When we're around the pile cap and we're in contact with the piles underneath the pile cap, there's a large increase by going deeper into the ground. Then this is looking at the width of the treated area, which has also a beneficial effect. So based on all these tests and the numerical modeling, we found out that there is we misunderstood the mechanism of how this was failing. The piles weren't pushing into the treated soil in this case. they were moving as a block. So I've exaggerated this displacement, but the piles were serving to reinforce the soil cement block. And as this moved to the left under the load, we developed passive force on the face of that block and side shear or adhesive resistance or skin friction, whatever you'd like to call it, on the side of the block. And when we started to analyze it this way, in terms of passive force and adhesive force, we were able to get good agreement with a simple model. And the unconfined compressive strength we found was relatively unimportant when we had the strength here higher than about 500 kPa. So our analysis procedure, we combined the lateral resistance from the pile group itself with the shear or adhesion on the side of the soil mixed volume and the passive force on the back face of the soil mixed volume. Our lateral pile resistance we obtained from a PY analysis that gives us the shear and the moment values in the piles. We calculated our side shear, assuming it would develop in about 6 millimeters of movement and then stay constant. And our passive resistance would develop with a horizontal deflection equal at about 3% of the pile cap height, H. Based on what we saw in the field in our numerical models, we developed a very simple approach. This is the zone, the effective width for passive force. We assume it comes out, spreads out at 45 degrees from the sides of the pile. And we are also assuming that the shear zone moves down at 45 degrees and that our height, the maximum height that we'll use is equal to the width of the pile group. Similarly, if we have a soil like this, we'll again use the thickness equal to the width and spread the load to the concrete face at 45 degrees. So the conclusions based on this study are that soil improvement really can significantly increase lateral pile group resistance. You don't need to add additional piles to get the resistance you might want. So we were seeing 60% increase for just a simple soil mix wall and a 80% increase for a jet grout or other technique that could get the treatment adjacent to the piles. The pile and the improved ground tend to act as a super pile, as a reinforced block of concrete. Our lateral resistance can be obtained from a simple model which accounts for pile resistance plus side shear on the soil cement block and passive force on the front face of the soil mix volume. And based on our calculations, it looks like soil improvement is likely to be less costly and time consuming than adding more piles and a cap in many cases. At least it's something that should be considered when we're trying to improve lateral resistance for pile foundations. That concludes my first part. Any questions that you might have about this? It's likely a lot of additional information coming to you in a foreign language. So I hope you were able to follow along.
Kyle, any question? maybe we can. Oh, there is a question from Auke Zagat, please.
Yes, hello, good morning. Thank you for this
Good morning.
Thank you for this very nice presentation, very interesting. I am Hauke Zagat from Technical University of Darmstadt in Germany. So
Yes.
My question is was about the finite element models you used there. Unfortunately, my connection was a bit broken, so I did not get which soil models did you use to model this pile test, because this was impressively good.
Yeah, this was Ud'A, was the computer model. This was done by Hubert Law and his assistant Joseph Chang at Earth Mechanics in California. They used a model that modeled the piles as a vertical column with spokes coming out to plates around the edges of the piles. And that model that they had could allow gaps to form behind the piles and allowed slippage on the front face.
Okay. Good. And the soil was modeled with what type of soil model? Do you know that? I mean, if you haven't done it,
I don't know the exact model that they use, but I just know the failure criteria and what they use to model their stiffness.
Yeah.
But the strength was basically the strength from our undrained shear strength profile. There were some small modifications that you need to do to get agreement, and then they used that same model for the parametric studies.
Okay. I'm asking because I really had in several projects with large pile groups, so with several hundred piles, the same question. Yeah. So how do we improve them? What is feasible? What can we use as the system to calculate this? That's also the question here for earthquakes. You modeled, so the testing was also done with cyclic loading, yeah, which is very interesting. So this is obviously, so now, okay, here you have the report. So this is all covered in this report?
Yes, and if you have further questions, then you could email me or Hubert Law, who are referenced in the report, and we could give you more details.
Okay, that would be great, because then we could maybe also use your models to calibrate some soil models, etc. Also for the cyclic loading, because this is, I guess, very challenging. It is.
Yeah. We focused on the monotonic part of the load deflection curve, honestly, but what you're saying is correct. The cyclic loading is often more critical for many applications.
Yeah, but seeing those tests is really interesting. So it's I'm a bit envious. So they really look nice. So thank you.
Thanks. We were fortunate to have a site where the soil conditions were really uniform, so we could make good comparisons.
Yeah, that's really good. Thanks.
Okay. I suggest to go to the next part, Kyle, and
okay.
for other question we can get later.
All right. Okay, for the second part of this webinar, I'm going to be talking about ground improvement for liquefaction mitigation. We know that liquefaction is a major problem in earthquakes throughout the world. It can cause damage to piles, like you see here in Niigata, Japan, where there was lateral spreading and the piles cracked at the interfaces between the liquefied and non-liquefied layers. We can have bearing capacity failure, like we've seen here in the Kocaeli, Turkey earthquake. We can have lateral spreading that causes damage to bridges, like we saw in the Limon, Costa Rica earthquake. And we can see lateral spreading at port facilities like we saw in Kobe, Japan, and more recently in the Port of Wellington, New Zealand, that causes damages to the port and the cranes that need to service the ports. I think something like 105 out of 126 of the berths were out of service after the Kobe, Japan earthquake, which resulted in $11.8 billion of direct damage, along with indirect costs that lasted for years and years. So there's a number of liquefaction mitigation strategies that could be imposed, and I've listed some of them here. We could use deep foundations to penetrate through the liquefied layer. This would be a good solution, but often it's more expensive, and we still have to be concerned about pile downdrag during liquefaction. We can densify the soil to prevent liquefaction by a number of strategies. Vibratory means, expanding resin injection, other techniques. This is a very common approach. We can also drain the sand so that water pressure doesn't build up as rapidly, and we can minimize the settlement potentially in this way. We can also partially desaturate the soil with some chemical treatments that might also be beneficial to increase the liquefaction resistance. More commonly now in the United States, we're using soil cement mixtures to create panels and columns that give increased lateral resistance to prevent liquefaction and settlement. So I'm going to focus on first on stone column treatment, which has been very common but can be a problem in certain cases. So the idea with stone columns is we can vibrate a probe into the ground, and then as it's withdrawn, we can inject gravel to create a dense column of stone, and this process is repeated on a grid pattern so that we also compact the soil within the area enclosed by the stone columns. Juan Bacz, as part of his PhD work, produced charts like this that give us the final SPT blow count relative to the initial SPT blow count for different improvement ratios. Here's 5%, 10%, 15, and 20. So as the improvement ratio, or the area of the stone column, becomes larger relative to the tributary area, you see an increase in the final SPT blow count, or you could do something similar to a CPT. Now, as the initial blow count increases, there's less improvement that's observed as part of the treatment process, because the soil is already dense to begin with. It becomes more difficult to compact it further. These curves are all based on sand with less than about 15% fines. So one strategy for looking at improving the lateral resistance of pile groups that may have been designed with inadequate capacity is to install stone columns around the piles to increase the lateral resistance, similar to what we were discussing previously. This strategy densifies the surrounding soil, increasing the lateral resistance of the pile. It provides reinforcement to the soil, provides additional drainage through the gravel, and it increases the lateral earth pressure coefficient, which also increases the liquefaction resistance of the soil. So in this study, we first did a test, which I'll show you here in a minute, with a 4-pile group reacting against a 60 centimeter diameter board pile. And then after we did that test, we added an array of stone columns, about 6 in this direction and 4 in the other, to create an improved zone, an island of improved soil around the test piles. The area replacement ratio in this test was about 14%. And to evaluate the performance, we used this blast liquefaction technique that I talked about in the last webinar, but I'll give a little more background here, where we detonate small explosive charges so that we can liquefy a large volume of soil, and then using a high-speed hydraulic ram, we can push the piles apart to see what kind of lateral resistance we develop. So when I first heard about this strategy, my mind went back to an old Western movie called Butch Cassidy and the Sundance Kid, where they were trying to decide how much dynamite to use to get the money out of the safe on this train. And I worried that that might be our problem. So we used licensed blasters, but I became even more worried when the blaster showed up at the site and said, "Good morning, my name is Butch." I started to worry if we'd gotten ourselves into trouble with this blast-induced liquefaction strategy. So here's our setup with the board pile that's reacting against 4 30-centimeter piles in a group. And these were connected to a frame so we could monitor the load carried by each pile. Here's a little video that shows that test blast. So after the blast, we didn't see much happening until we started loading the pile laterally. And that lateral load created enough of a gap with water pressure to actually flow to the surface. We were pretty excited because all our sponsors were there. And if this didn't work, that would have been the end of our project. So we clearly liquefied the soil, and there was a dramatic decrease in lateral resistance on the piles as a result of that liquefaction case. This shows some photographs of the vibratory section of the stone column device probe, and this is the hopper that we put the stone column in. Here you see the stone being dropped into the hopper, and then this is injected under pressure into the ground as the stone is withdrawn upwards. So these plots show the cone tip resistance before treatment, which was on the order of 4 to 5 megapascal, and then after treatment, where there's a tremendous increase, and now we're between 10 and 30 megapascals. So this was a site with loose material that was just ideal for treatment. Our typical blow count, SPT blow count in these areas was 11 to 12, or 10 to 12. And with the area replacement ratio, we'd expect to be within this green zone. to see an increase to about 30. And that's about what we got. That's our typical result. You saw the picture without stone column treatment where the soil liquefied and water flowed to the surface. Here's a photograph after the same charges, actually more charges throughout the whole zone after the improvement. So we couldn't liquefy the soil for any significant period of time. This shows the load deflection curve prior to liquefaction and then after liquefaction. And you're seeing about 9 times more movement to develop the same resistance here and displacements of about 225 millimeters. In contrast with soil treatment with the stone column treatment, we see a much stiffer response from the soil. This plot shows the excess pore pressure ratio after blast-induced liquefaction, and water pressure is staying higher than 60 to 80% for 10 minutes while we're cycling the load back and forth. In contrast, with the after stone column treatment, we had some peak loads or peak excess pore pressures between about 45 and 70%, but they dissipated very rapidly in comparison to the untreated soil. If we compare the settlement with the stone columns, when we liquefied the soil, we had about 200 millimeters maximum settlement in between the 2 pile groups. After stone column treatment, there was no measurable settlement, so it's less than the accuracy of our survey, which was about 0.25 millimeters. So a tremendous advantage of having the stone column treatment around these piles. So the conclusions relative to this relatively clean sand is that stone column installation significantly increased the density of the sand around the piles. The excess pore pressure generation was reduced. The rate of excess pore pressure dissipation was increased, which is very beneficial. And the stone columns increased the post-blast stiffness by about 300%. So this turned out to be a very beneficial strategy for dealing with a foundation where we needed some increased capacity, but didn't want to go to the trouble of putting extra piles in place. Now this stone column treatment works very well when we have sand with fairly low fines contents, usually less than about 10% fines, as suggested by Jim Mitchell in his state-of-the-art report in 1981. But many times we have to deal with higher fines contents in reality in our work. The fines tend to reduce the permeability, which doesn't allow the soil to compact as quickly, and the fines tend to strengthen the soil structure, which prevents it from compacting as efficiently. But if we have a soil profile that has a fines content in this region, we may still need to improve it to some degree, and we might have some problems with regular stone column treatment. So one strategy that we've looked at and we're going to explore in the rest of this presentation is looking at stone columns with prefabricated vertical drains or Wick drains. So prior to installing the stone columns, we put these PV drains between each of the columns and then vibrate the column into place. And we find that when we're doing this, water moves horizontally to our drains and then comes to the surface. Now, in order for this to work, the drains need to be within about 1 meter of the treated zone. And this becomes more important as the soil, as the fines content increase. So this shows a large area where we've first put PV drains in place and then are putting stone columns, treating the soil with stone column rigs. There are a number of case histories where we can get some information about how this works with materials that have higher fines content. One site is Salmon Lake in Washington State, where 1,060 stone columns were in place to a depth of 20 meters, along with 32,800 meters of wick drain. This was in connection with improvement adjacent to an earth dam where there was concern about liquefaction. The pre-treatment conditions are that we have two materials, a silty sand with an SM classification, average fines contents of 49%, average clay of 5%, and the average pre-treatment was about 22. This is the clean sand equivalent. And the silt layer had a fines content of about 65% with average of 11% clay and a pre-treatment blow count of 17. So prior to improvement at Salmon Lake that was done by the U.S. Bureau of Reclamation using 90 centimeter stone columns with a dry bottom feed method where they're using air pressure to inject the stone. These columns were installed in a triangular arrangement with 1.6 meters center to center spacing. And then the area replacement ratio was much higher than we saw at Treasure Island. And you'll see in most of these case histories, we need to have an area replacement ratio of about 20 to 25% in order for this to be successful. Here, wick drains were placed between each row of stone columns prior to the treatment. So what was the result? This was reported in an article by Luring in 1998. This boundary shows the zone that the blow count that they were trying to achieve. And the average pre-treatment value was just a little higher, leaving many of the data points below the range that they needed to have. The green line is the average after treatment with the wick drains in place, and there are very few data points falling below the boundary for liquefaction after treatment with this approach. So in the sandy silt and silt, where our blow counts are 12 and 17 before, post-treatment it increases to 33 and 23, which represents an increase of 90 to 95% in these materials, which is much higher than you would initially suspect. So it appears that the drains being in place has really had a profound influence. We had an opportunity to do tests, additional testing here at a site in Utah, Shepard Lane, and you can see that while we were installing drains in one location, water was coming out of the drains in the other adjacent locations. So you can see that the drains are being effective in relieving pressures. Here's another view of water coming out of the drains while we're installing and treating the soil adjacent to it. Here's a video of this. So the stone columns are being treated and being formed over here. Wick drains. So let's look a little more closely at this site. It has about 25% fines in the upper, these are in English units, but in the upper 4 meters. And then below that depth, we see fines contents that are increasing up to 40%. Clay content in the top layer is about 9% and increases to maybe 12% in the lower portion of the profile. In the previous test by luring, we didn't have a comparison between sites with and without drains, so we divided our test site into 4 areas and did some with drains in place at these 2 quadrants, and then did treatment with no drains, stone columns only, on the other 2 quadrants. Here we're using an area replacement ratio of 26%. The diameter of these columns is 1.07 meters, and the spacing center to center is 1.8 meters. So this plot shows the average values at every 1.5 meter interval. This is before treatment in red and after treatment in blue with the drains. So you can see we're seeing a substantial improvement with drains being put in place. Without drains, the improvement is considerably reduced, and in many cases, particularly in the finer layer of soil, there's no improvement at all in the deeper part of the profile. Our pre-treatment blow count in the zone from 0 to 6 meters was about 18 to 19, with average fines contents about 28%. Our post-improvement blow counts were increased substantially. This represents an increase of 148% in the top 6 meters, but only 35% in the bottom. And the standard deviation, despite the improvement, the standard deviation in the blow counts was quite high. So you are going to have to deal with this kind of variation for problems like this. Look at the case in the deeper part of the profile where we have a higher fines content and more clay. We didn't see as much improvement. The improvement is 70% with drains, but almost nothing with drains. And we're still seeing the same variability and scatter in our data. So what we're seeing here is that there's greater improvement and higher final blow counts in the drained areas. This improvement is lower when the fines content is higher. We also see that there are relatively high final blow count standard deviations that we need to account for. We also did some tests looking at the increase that, in the change in blow count versus the initial blow count. You're seeing some increase that's more substantial at low blow counts and decreases with higher values, as we were expecting to see. These are plots that show the improvement in blow count with time. These are the original blow counts before treatment. The green plots are 2 days after treatment, and the red curves are 13 days after treatment. So you can see that there's a substantial increase in the blow count with time after treatment for these sites where drains were used. In this zone, it's pretty substantial as well. There are a couple places where there was very little improvement, and that's these zones where the clay content was greater than 15%. So in our case histories, we were unlikely to get much improvement where we had more than 15% clay. Now, when it came to the sites without drains, we didn't see this improvement with time. fact, it stayed basically the same with time, only small variations. This is another way to plot this. It's the final blow count on the y-axis and versus the initial blow count. This is 1-to-1, no improvement. This is red curve is 1 to 6 days after treatment, and the blue curve is 7 to 14 days after improvement. So we're seeing a large improvement with drains, but there is, again, a scatter in data that has to be dealt with. Here again is the improvement versus fines content, and they're just showing this trend line down, but again, a lot of scatter. And when you have more than 15% clay, you're usually in the improvement that's less than 5%. So based on the compiled, we've taken a number of case histories now for 15 to 20% fines with area improvement ratios between 10 and 15%. This is the zone of improvement you could expect to find as a function of, or the blow count you could expect to find based on your initial blow count prior to treatment. As the fines content increases, you need to have higher replacement ratios. And they're now about the same. With these larger improvement ratios, you're getting about the same improvement that we would have if the sand was clean. And these again are with drains between each of the stone columns. Here again is effective fines content on improvement with cases where we had about 26% area replacement ratio. We're getting less improvement as the fines content increases. So some of the conclusions regarding stone columns with PV drains is that despite having high fines contents, greater than 20%, the blow counts can still be increased if we use PV drains to improve drainage during installation of the stone columns. We're seeing improvements still of 50 to 200%. You need to expect significant scatter, 30 to 40% coefficient of variation, owing to the connection between the fluid flow properties of the soil and the fines content. Despite the presence of wick drains, improvement still decreased as fines content increased and was ineffective when we had fines content with 15% or more clay. For sites with drains, blow count continued to increase with time, so it may make sense to test not just immediately after treatment, but maybe a couple weeks afterwards. And there's some design guides here that can help designers trying to deal with soil improvement with high fines content material. How are we doing? I wanted to show one other treatment that we'd used. This is colloidal silica grout, where you have a loose sand. This allows you to use grout and inject silica by permeation into the void space. The silica is fine enough, micro silica particles are fine enough that it can go into the soil and basically creates a gel-like structure that gives the soil some cohesion. The advantage of a technique like this is that you can treat under existing structures where you would not be able to use something like stone columns or dynamic compaction. And you can use the groundwater flow or injection and pumping wells to move your material into place. These nanoparticles have an average size of 7 nanometers, and they can, as a result, can penetrate voids in sand. With 5% by weight in solution, it has a density and viscosity similar to water. And you can control the gel times from minutes to months based on the pH and salt concentrations that are injected. So these show from lab tests different gel times that you can use to allow the silica to move into the soil profile and then solidify with time. So I did this set of tests with Patricia Gallagher at Drexel University. And this is a plan view of the field grouting program. So each of these circles represents an injection well. And then we had an extraction well at the center. So these are a distance of about 5 meters away. And she would inject the grout to treat towards the center. So in profile view, the liquefiable sand we were expecting to originally treat was 8 meters thick. So what we do is put some packers down the hole to inflate against the side, and then we can inject the silica grout into the soil. I'm sure it went just like that. No, I'm sure there's some variation of this, but this is an illustration. And then we moved the packers, put them back into place, and injected another segment. So the zone that we treated was only 2 meters thick, and we're going to liquefy an 8 meter thick zone in comparison to this. So we used blast charges, 1.5 kilogram charges at 6.4 and 8.5 meters that would liquefy or see what would happen to the grouted sand and the liquefiable sand. We had settlement rays coming out from the center of the blast zone so that we could compare the settlement with and without grout treatment. We had piezometers located at 6.4 and 8.5 meters. So in the treated zone and in the untreated zone. Now you may be surprised to learn that in both the treated soil and untreated soil, the blasting produced liquefaction. So we have an excess pore pressure ratio equal to 1. But the performance of the two layers was completely different, because in the zone treated with silica, nanosilica particles, we turned the soil into more of a cohesive material, so the generation of pore pressures didn't reduce the strength. And as we compare the treatment with grout and the treatment that's ungrouted, we're seeing settlement on average reduced by about 25%. So that's consistent with the treated zone that we'd grouted, which is also about 25%. So this appears to be a relatively effective treatment for the cases where we have existing infrastructure. And because of the high cost, this would probably be the only case where you'd want to use this technique. Silica grout's capable of penetrating sand under field conditions. Pore pressure development is only slightly reduced during an earthquake or during our blasting, but settlement was nearly eliminated in the zone that was treated with this silica grout. I've put some references in here to silica grout and some other places, I'll give some additional references later on. This is a photo of our campus in the wintertime. We have some really nice ski resorts close to our campus, so hopefully sometime you might get a chance to visit us and we can go skiing together. Questions?
Thank you, Kyle, for this second section. It's very interesting. There is anybody with any other question? I I have a question, Kyle, on this part, if I can. It's a more general question. Which is the influence in cost when you add the drains in a ground improvement treatment?
It's a good question. The drains are one of those things that has actually decreased in cost with time. So I think in the United States now we're looking at maybe 40 or 50 cents per from a dollar. So maybe 50 or 60 cents for a euro per 30 centimeters of drain length. So it's relatively inexpensive to put the wick drains in place. Mm-hmm. It adds extra time to the process, but the comparison is that you can get improvement in cases where you would have a hard time getting improvement otherwise.
Okay, thank you. We have other two questions. One is from Madhusudan, and the second is from Jose Antonio Fernando. Please, the first.
Hello, sir, Professor Rollins. It was a wonderful presentation.
Thank you.
I have a question. The earlier part of the presentation where the charges were used for blasting and yes, liquefaction was induced, the reaction piles would also move, I guess. Does it have an implication on the measured data?
Yes, this is a good question. So we have an independent reference frame that we're using to monitor the displacement of the piles. So even though the reaction piles move, we monitor the net movement of the independent movement of each pile and each drilled shaft, or each bored pile.
Yeah, thank you. I have another question. So you showed the results for clean sand where fines content was less than 15%. Yes. In general, stone columns used for treating the soft clays. So would you recommend the pile and stone column combinations in soft clays? We have received a project on that. Do you have any comments?
I know that stone columns are used for reducing settlement, vertical settlement in soft clays. So this would be desirable. From the tests that we've done with geopiers, rammed aggregate piers in clay, the improvement in lateral resistance that we're seeing was fairly small. So I don't think that this would increase the lateral resistance in clay more than maybe 10 or 15%. It would be a small improvement. The cases where we're looking at this is where you're using stone columns to densify soil that might be liquefiable.
Thank you. Thank you, Professor Rollins.
We have another question from Jose Antonio Fernandez.
Hello, good morning. Can you hear me?
Yes.
Okay, thank you for the presentation. I have one question about the Salmon Lake case. You showed that the depth of the stone columns were 20 meters.
Yes.
And, I was wondering about it is related to geotechnical consideration or the limitation of the drilling machine, because when you show the SPT profile, they were quite constant. Can you say something about this?
Yes, it becomes a little more difficult to improve soil with stone columns below a depth of 20 meters, because then you start to have reduced effect of your oscillations. It can be done, but it becomes more time consuming.
Very expensive, perhaps, no? The machine, I think it's quite expensive, no?
Yes. And I think that's the main reason. Also, the major zone that was liquefiable was in that range at this site.
Okay, but can you be aware about liquefaction under these 20 meters or not?
I'm assuming that it wasn't a major problem because they didn't try to treat any deeper than that.
Okay, thank you very much.
Thank you. Kyle, I think we can go to the last part.
Okay. All right, this last segment is dealing with prefabricated vertical drains for liquefaction mitigation. This is more of a research effort, although they are being used fairly widely in the United States. So we've talked about the fact that you can use vibrocompaction methods, vibratory methods for improving liquefiable sands, like stone columns, dynamic compaction, compaction grouting, other techniques like this to densify the soil. But it's also possible that we could have liquefaction mitigation by drainage. This has been a concept that's been out there for many years. The idea is to put vertical drains in place, and when earthquake starts to generate pore pressures in the ground, the water can move horizontally to the drains and then exit without creating problems for the soil. In the past, that's been done with gravel columns, but the gravel is not as effective as a drain pipe with slots at 4 or 5 locations around the perimeter of the pipe. And then you can use a filter fabric to prevent sand from entering the pipe. And these are much more efficient to, also for installing. So some early research by Lionel Bacz said that as long as you can keep the excess pore pressure ratio, R sub U, less than about 40%, you'll have a relatively small volume. If you get higher than this, then the soil compressibility can dramatically increase and lead to large settlements as a result of liquefaction. So let's look at how this would how these would be installed. This is we first have a hollow steel pipe or mandrel. The drain pipe is moved into the mandrel, and there's an anchor plate at the bottom. Then this pipe is brought to the soil, top of the soil profile, and vibrated down into the ground. Once the drain is in place, then you can withdraw the steel pipe, and you can see installation like this to 45 meters, about 17 meters in about 3 minutes. So it's a very rapid installation process. So because of some of our research, this was used for treating liquefaction problems on the San Francisco-Oakland Bay Bridge approach fill. And you can see that installation process. So here are the drains. There's the anchor plate. This is the vibratory pipe with 3 fins to improve compaction during installation. Let's put it in place. Move to the location where it needs to go. You can see that as the vibration intensifies, the ground starts to settle around the pile. So not only are you getting the benefit of drainage, but you're also compacting the soil in the process. So you can see this is a relatively efficient approach. Some of the potential advantages of vertical drains is that you can reduce the cost of installation by 50 to 70% in comparison to conventional stone columns. There's a much shorter installation time. It might take 40 minutes to compact a stone column, where you saw those go in 3 minutes. It's not necessarily required to evaluate improvement, although you could, because you're relying on the drainage. There is nevertheless densification during drain installation, so that you have this benefit. Because of the hollow center on the pipe, there's much greater flow capacity into these drain pipes that were maybe 75 millimeters to 100 millimeters than you would have from a stone column. And there's reduced potential for a water layer formation in layered soils. What exactly do I mean by that? Well, sometimes you might have an embankment that has a silt layer at the ground surface and a liquefiable sand underneath it. If this soil starts to liquefy and water comes to the surface, it might be trapped by this silt layer, prevented from coming to the surface, and failure could occur through that water inner layer and cause a landslide or lateral spreading. If we put vertical drains in place, this would allow the water to drain to the surface and not be bound by that silt layer, and hopefully prevent the problem from lateral spreading from occurring. So our objectives in our study over the years has been to try and evaluate the ability of these vertical drains, they're sometimes referred to as earthquake drains, to reduce excess pore pressure and settlement. We wanted to define the influence of the drain spacing on the drain effectiveness and provide well-documented case histories which could be used to calibrate and validate numerical models, because we really need something like this to help us design effectively. This is the first installation that I was connected with. It's a drain installation on the island of St. Lucia in the Caribbean. If you have to do a test project, this is a good location to do it. We were monitoring the improvement with a cone penetrometer at this site. Can you see this mountain in the background? These were being installed for this Sandals Grand St. Lucian Beach Resort, which is currently occupying that test site. A few years ago, there was an earthquake close to this island, and they called me to ask if I would go see how the drains performed. Here's a word of advice for you. If someone asks you if you'd like to go to a Caribbean island, the answer is always yes. Just say yes. I'm too much of an engineer, so I looked to see if that distance from the earthquake fault to this island was far enough away that it would not liquefy. And I concluded that it was far enough away that there wouldn't be a liquefaction problem, and so I missed out on having a second trip to this island. Don't make that mistake. The PV drains we've also talked about were used for this new section of the Oakland-San Francisco Bay Bridge. Here are the drains for the approach fill being installed. Like you saw, 17,000 drains produced up 10 to 15 centimeters of settlement during installation. And then they come up to an elbow, and the pipe moves horizontally into a gravel layer. So this is this permeable gravel layer. The drains come up to that and then can move out into the San Francisco Bay. This is the zone that they were trying to treat. It's 3.5 to 6.5 meters thick and marginally liquefiable. So they thought the earthquake drains or the vertical drains would be a good solution. So how do you evaluate the effectiveness of these drains? Ideally, you'd want to have them be subjected to an earthquake like that site on the Caribbean island, but we don't have a case history yet for this. So we've used controlled blasting. Other researchers have used vibro-size testing and centrifuge testing. And then more recently, we've used shaking table tests. So some of the controlled blasting sites were at locations in San Francisco Bay, on Treasure Island, and in Vancouver in British Columbia. This is the Treasure Island test site. It's a man-made island in the center of the bay. That's the test site, and here's San Francisco in the distance. The soil profile at this site consists of fine sands and silty sand, extending to a depth of about 6 meters, which is underlain by siltier sands. The cone resistance is about 8 megapascals. The blow counts are from 7 to 15. And if you convert to relative density, you find a relative density of about 50% in this zone that we're going to be testing. The settlement during drain installation was substantial. You can see that there was a group of 8 drains, and these are 75 millimeters in diameter that were put in place. And then these depressions were filled with loose sand. This shows the settlement with just wick drains, which is not very much, but in the zone where we vibrated the soil, or vibrated the drains into place, we're getting very large settlements, settlements of maybe 20 to 30 centimeters. We did one test where there was no vibration, and of course the settlement was much reduced. While we were installing the drains here and installing the drains here, seeing the settlement, we could see water flowing out of the adjacent drains at 1.2 meters away. So we did a test with and without drains, with blasting, and the induced settlement in the untreated area is shown here. So we're getting something greater than 80 millimeters, maybe as much as 100 millimeters in the untreated zone in the center here. Then we did the testing after treatment, and we've have some arrays here with wicks and clusters of these larger diameter drains. And in the area that we've treated up here with drains, we're seeing settlements that are limited to 20 to 40 millimeters. We're still seeing some zones here where there's higher settlements, and we believe that this is associated with settlement of the loose fill that we use to backfill the depression in the soil. But you can clearly see that there's much more settlement in the zone that's not treated with drains compared to what was treated with drains. So this is showing that comparison. So we had this one site was giving us some good information. This is showing the excess pore pressure. For the untreated site, we had pore pressures up as high as 90% of the vertical effective stress, so essentially liquefied, and they might take 10 minutes to drain down to 60% excess pore pressure ratio. with the earthquake drains in place, we had a very short spike with rapid drainage of the soil surrounding the drains. Then we started to get some increase, and we found out what was happening here is the filter fabric was allowing sand to fill in the pipe. So be careful, because not all the criteria for infiltration are very accurate. So we had to go to a more stringent requirement. This is a second test site in Vancouver, which you can see off in the distance here. As you come along the road to the Fraser River, if you're a structural engineer, you might think this would be a good place for a bridge. But if you're a geotechnical engineer, you might say this would be a good place for a tunnel. And actually there is a tunnel there, the Massey Tunnel, that goes underneath the Fraser River. And they allowed us to do testing at this tunnel portal section, which had very uniform clean sand. So we've got some silty material and clay material down to about 5 meters. Then we are going to treat, we're going to try and induce liquefaction from about 5 meters to 12 meters in this soil that has a relative density of about 40 to 45%, maybe 40 to 50%. This was a big concern. Liquefaction was a big concern here because the tunnel, the numerical evaluations suggested that even if they compacted the soil around the tunnel so that it would not liquefy, the tunnel would still float upward. And the problem that they were having is that the volume of water in the untreated soil would flow into this, even this densified layer, and cause the whole tunnel to float upward. So their strategy was to put some vertical drains at the edge of the improved zone, so that the water that came in here would have a chance to flow upward and get out of the profile. So we're treating a much larger area with the composite drains, I'll call them, and then using 4 blast holes to induce liquefaction, and we compared that to a site with no drains adjacent. So again, installing the drains produced 30 to 35 millimeters of settlement. This is the edge of the drain cluster. So even at the edge, we're getting maybe 18 centimeters of settlement. And then we're going to set off these explosive charges around the treated zone and the untreated zone and see what happens, see if the drains work. So our primary function here was to see if the drains would carry enough water to keep the treated soil from liquefying. So take a look at this video and see if you think the drains can carry enough water. We were all surprised at how rapidly this silty sand. Within about a minute, all the drains had stopped flowing because they had rapidly allowed the soil, the water to dissipate. These plots show the pore pressure measured, excess pore pressure ratio measured in the treated soil adjacent to the, or in the undrained soil compared, in the untreated soil compared to the soil with the drains in place. Here you see excess pore pressures around 85 to 90%, remaining in place for 4 or 5 minutes. With the drain, we have a spike in pore pressure which rapidly dissipates down to values which are inconsequential. We were a little surprised that the settlement wasn't reduced more, but we saw a reduction in settlement with the drains of about 40% in comparison to the zone without drains, or the untreated area. And that zone that was treated with drains had a very uniform settlement profile in comparison to the untreated area. We used a computer model called FEQ Drain, developed by Juan Pestana at UC Berkeley, to analyze this event, and it allows for axisymmetric analysis around each drain pipe. And we first tried to calibrate our model with what we measured in the blast test, and we're getting 300 centimeters of settlement. And then we used that calibrated model with the various earthquakes, which would take much longer to develop the pore pressures. And you can see that there's a substantial reduction expected in the settlement that would occur. But this again is just numerical modeling, and we want to know what really happens. Although we believe the model, we want to verify it. So some more testing, vibro-size testing that was conducted by the Rathje at University of Texas with this early version of their vibro-size truck. This loading system produced 20 hertz of loading for a little over 3 seconds. And they did a test with no drains. This is a 1.2 meter cube of soil with clay all around it, and then a test with a drain at one end of the treated area. And they're monitoring the pore water pressure that develops and also monitoring or interpreting the shear strain that's produced. There's no compaction performed on the sand. It has a relative density of about 40%. So with no drain in place, the vibro-size shaking produced liquefaction in 3 seconds, but that's about 60 cycles of loading with this shaker. And you're seeing the shear strains of about, plus minus 10%. In contrast with the vibro-size shaking, the same level of shaking for the same amount of time, the excess pore pressures on average only got up to about 25 or 30%. So this test has some problems. There's not a potential for the water to flow in from the edges and contribute more water to the zone that you're testing, but it gives us hope that this method might work. There was also some centrifuge tests done by Marinucci at Georgia Tech University in connection with tests at the centrifuge at Rensselaer Polytechnic Institute, RPI, in New York. So this is a yellow sand, 40% relative density, and they're doing a test with no drains on one side of a slope coming to a river, simulated river, and then some vertical drains that are spaced at 1.5 meters on centers. The liquefiable layer is 5 meters thick, and they have a 3-degree slope here on both sides. Here you see some photos. These simulated drains in the centrifuge are more like straws, little small rubber tubes. Then the sand is pluviated into the ground around the drain pipes. So there's no densification in this process. Only drainage is involved, no compaction of the soil. In the untreated soil, with 10 seconds of shaking, you've liquefied the entire profile. In the treated soil, even after 10 or 20 cycles of shaking, we are only at about 70% excess pore pressure in the top 3 meters of the profile and maybe 50% in the lower part of the profile. So the drains were doing what they were supposed to do, reduce the excess pore pressure. Now, what effect did this have on horizontal and vertical displacement? The horizontal displacement was dramatically reduced. So in the untreated area, we're getting lateral spread that produced displacements of 60 centimeters on the prototype scale for a peak ground acceleration of 0.28 g. When the drains are in place, the displacements are reduced to maybe 10 centimeters, which might be acceptable for some structures. In terms of vertical settlement, without drains in place, we have 30 centimeters of settlement, and with drains in place, we're at about 15. So they've reduced the settlement by about half, by about 50%. Another important finding of this study was the settlement or the horizontal displacement increases the longer the liquefied soil remains with a pore pressure higher than 50%. So this is the horizontal and vertical trend lines. So this suggests that if we could reduce the pore pressures quickly, we would have less settlement and less lateral spreading. I think this makes sense. The longer the soil stays liquefied, the more the soil structure can deform and strain and cause problems for us. It's best to dissipate the pore pressures very rapidly. The last test we'll look at is the shaking table test that we conducted recently with a laminar shear box. So each one of these rings of aluminum are able to roll on the on bearings of the ring below it. So we have these high-speed actuators that are going to push the bottom ring, and they'll push against this reaction wall, and then the whole box is on rollers so that it can slide. The sand is compacted or is placed inside this laminar box with a liner so that it can liquefy. So here's my little animation of that process. It can deform like the soil would. So this is the laminar shear box at the University of Buffalo. It's 6 meters tall, and each one of these rings are 15 centimeters thick. So you can approximate the behavior of the soil as it liquefies. These are the hydraulic actuators that can push on the bottom ring and cause everything to start shaking. So we did tests with vertical drains in place, 90 centimeter spacing and 1.2 meter spacing. We used a clean uniform sand with a D50 size of about 0.2 millimeters. We subjected the sand to 3 levels of shaking, 0.05 G, 0.1 G, and 0.2 G, and then conducted 3 rounds of tests with these 3 acceleration levels. This is a photograph of the drains with the filter fabric in place, a better filter fabric now. And this sand would be hydraulically placed at a specified height of 30 centimeters above the water level. And then these are, so there's no compaction of the drains in this test either. So we took buckets of sand as we were filling them and pulled them out to get the relative density. So we start out with the relative density of about 25%. And as we do each test with higher accelerations, we can watch the relative density increase. So the second set of tests were at 50% relative density, and the last were a little higher than 60%. So we had vertical arrays of pore pressure measurement of pore pressure transducers. We had settlement measured at the surface and settlement measured versus depth. We have accelerometers and displacement transducers at 30 centimeter intervals on the wall. We have a seismic CPT profile for each round of testing, and we have borehole permeameter tests that are telling us that the permeability or hydraulic conductivity is between 0.04 and 0.07 centimeters per second. So it's fairly high permeability. So here's a test. I was wondering if the drains would work as well as they did in the field, where we saw this huge volume of soil. So this is the first round of testing with an acceleration level of 0.1 G. Before I do that, I ought to tell you that this whole test took place in 7.5 seconds at a frequency of 2 Hertz. We did this so that we could compare with other tests that had been performed at the same frequency with no drains in place. But in a real earthquake, the drains would have much more time to function. So this was a very stressful application of shaking for the earthquake drains. Okay, the shaking is stopped, and within a few seconds, all the water stops flowing out of the drains. So they were highly efficient in removing water from the test site, or from the sandbox. This is with a peak acceleration of 0.2 G. Oh. I just could not believe how fast the water could exit from these drains. Okay. This is the perfect case where we have clean sands. Now, what are the results? With no drains in place, the entire profile liquefied. With drains in place, we see excess pore pressures of about 75% at the surface depths of 1 meter and 2.5 meters, but it didn't exceed 50% at 3.2 and 3.9. So the drains are becoming more effective at greater depths. I think this has also been shown from some numerical modeling, which gives us some hope that we can do a good job with our numerical models. We saw full dissipation in about 5 seconds with the drains in place after the shaking stopped versus 90 to 200 seconds without the drains. So reducing that time of liquefaction is also beneficial, as we discussed earlier. The peak excess pore pressure is also shown here for each round of testing. You can see that with each round of testing we're seeing a rapid decrease in pore pressure ratio with depth. We're seeing better reduction in pore pressure with depth than at the ground surface. So it may make sense to do a combination of some shallow ground improvement technique near the surface and drains deeper down. The drain performance improves somewhat as the sand density increases with the later rounds. So overall, we plotted the settlement for each one of these tests and compared this to the cases without drains. We have 2 cases to compare against, one with 0.1 G shaking for 8 tests, and one with 0.1 G shaking for 6 tests, followed by 0.2 G for the final 2 tests. And if you look at the drains, our drains, there is a pronounced difference in settlement, maybe 30 to 40% reduction in settlement depending on where you look. And this again is the case with no densification during installation. We also plotted the pore pressure ratio versus the shear strain that was produced. This is what's produced without drains in place. This is what we're measuring with drains in place. So for the same cyclic shear strain level, the drains are keeping the pore pressures much lower than we'd expect them to be if no drains were in place. So some conclusions with regard to the drain. The vertical drains were effective in reducing excess pore pressure in comparison to the case with drains, and the drains were more effective at greater depth. The drains carried large volumes of water to the surface and eliminated any sand boils which were observed in some of the tests without drains. Now that's quite important because in New Zealand, they found that about 30% of the settlement was a result of sand ejecta. So the drains could be very beneficial, very positive here. There was complete dissipation in just a few seconds with the drains relative to 1 to 2 minutes of liquefaction without drains. And this is very important for lateral spreads. If we can prevent the soil from staying liquefied, we can prevent the soil from straining laterally. There is a significant reduction in RU for a given shear strain, and settlement is reduced with the lower RU. The drains did not eliminate pore pressure entirely in ARC tests, but they did reduce settlement by about 30 to 50%. These results are similar for the blast test that I've shown you, for the centrifuge test, and the shaking table test. So I don't believe there's some strange thing. I think this is very typical. And if we can get our numerical models to agree with these results, I think we can have a design procedure that would be very effective. I see we're up on our time. What do you think, Sarah? Should I show this last New Zealand?
Yes, I think we can have, how long is the last part, Kyle?
I think 5 or 10 minutes. 5 minutes, let's do that.
Yes, I think it's good to conclude.
Okay. So one of the other strategies for dealing with liquefaction is suggested here by our friends in New Zealand. They suggest improving a layer of soil maybe 4 meters thick and then allowing liquefaction to occur in the deeper part of the profile. This could be used for some buildings such as houses where we're just trying to minimize the distress to the building itself. So the improvement techniques, the idea is that this improved ground may prevent ejecta from coming to the surface and will cause the building to settle more uniformly, even if liquefaction occurs down here. So they used a variety of improvement techniques like rammed impact compaction, displacement piles, rammed aggregate piers, low mobility grout, and soil cement and gravel rafts. We did blast liquefaction testing to liquefy the soil underneath the treated area to see how the whole system would behave at this site where houses had been condemned after the New Zealand earthquake sequence in 2011 through 2013. So here's the blast test from this situation. We're looking at different improvement strategies at each one of these locations and compared to a non-treated area. So we're looking at a few hundred kilograms of explosives detonating there, which produced liquefaction and sand boils in areas that were not treated at all, some large ones in fact. And the idea here is that we could reduce the differential settlement, even though we might get some large total settlements. And the rammed aggregate piers were very effective in reducing the differential settlement relative to other techniques here and here. And also some of the gravel mat foundations were effective. Even though there was a lot of settlement, there was very little tilt and differential movement. So this might be a new strategy that could be used to reduce differential settlements in the future for a very low cost. I've put also some references here for PV drains, for stone columns, and that should be it. Anything left? It looks like we're out of time, but maybe there's a question.
Thank you, Kyle. There is anybody with any question or comments? Okay. So probably people do the question during the other two parts. So
Okay.
I think we are at the end.
All right. If there are any questions that you have.
Sorry, there is a question.
Oh.
There is Sri Kant that would have a question for you.
Professor,
Okay.
thank you for the presentation. The question I would like to ask is, can we use this, am I audible? Hello?
Hello? Yes?
Am I audible, sir?
I didn't understand what your question was.
No, am I audible?
My article.
Yeah, the question is, can we use blasting as a method in this? I mean, for this ground improvement along with your PVDs?
Yes, this is another method that I didn't have time to talk about, but you can also use blasting just by itself as a method for improving the ground and compacting the soil.
Okay.
And if you have layers that are silty or clayey or a surface layer that might impede the process, you can put drains in place, and this makes the compaction process more effective with even controlled blasting techniques. Yes, so we weren't trying to really compact the soil necessarily with the explosives. We're trying to evaluate the performance of the system with small explosive charges, smaller than what you would use for compaction with explosives.
Thank you very much, sir.
Thank you, Kyle. And thanks for giving this second presentation today from the Department of Engineering Geology, and to are available to answer to question. Eventually there is any other person who would like to write you. Okay. So we can conclude this second webinar, and thanks all the people for the participation. Bye-bye.